Good morning, good afternoon, good evening. Thank you all for joining us, the IEEE CASS Rio Grande do Sul chapter YouTube channel. So we are here to have another exciting talk by Professor Volkan Kursun from Norwegian University of Science and Technology in Norway. He's going to talk about ultimate field effect transistors with 3D stacked nanowires. So today we are going to see the talk by Professor Volkan Kursun from Norwegian University of Science and Technology in Norway. He's talking about ultimate field effect transistors with 3D stacked nanowires. So Volkan is a professor. Yeah, he holds a PhD from University of Rochester in New York, and he's now a tenured professor at the Norwegian University of Science Technology in Norway, and he also held some tenured track faculty positions at USA, Hong Kong, Japan, China, and Korea. That is very impressive. So his research interests are in the field of heterogeneous 3D integrated systems on chip for neuromorphic engineering, advanced information storage and process technologies, no volatile edge computing for the Internet of Things. It has more than 170 publications and nine patents, USA and China patents, on novel high-speed and low-power semiconductor devices and integrated circuits. He is also author of a book, Multi-Voltage CMOS Circuit Design, and he is a senior member of IEEE. So thank you, Professor Volkan, for accepting our invitation. It's a pleasure to have your talk in our chapter channel. And now the floor is yours for starting
Claudio,
that.
thank you very much for the introduction. And I would like to thank Professor Ricardo Rage, for inviting me to give this talk. I really appreciate it, Ricardo. Okay, so the title of my talk is Ultimate Field Effect Transistors with 3D Stacked Nanowires. So let's talk about the title first a little bit. Why do I call it Ultimate Field Effect Transistors, these 3D Stacked Nanowires? There are two reasons. First of all, FinFET, which is the current standard transistor technology used by the semiconductor industry, is very rapidly running out of steam with technology scaling, as I will talk in detail today. So that's why people like me believe that this transistor FinFET is going to be soon replaced by something better. And I strongly believe that 3D stacked nanowires, nanowire-based transistor structure is the best candidate. And so the scaling of the CMOS technology, of course, is also approaching some limits because of material limits of silicon, as we all know. So I believe that at the end of the technology scaling roadmap, basically, these are the devices that we're going to be seeing in our computer systems, for instance, okay? So that's the first reason why I call it ultimate, these devices, because they're going to take us to the end of the scaling roadmap, in my opinion. And the second reason why I call them ultimate field effect transistors is because the field effect is strongest. The best field effect you can ever get is possible in these 3D stacked nanowire structures. The field effect is much stronger than FinFETs, much stronger than the older planar single gate MOSFETs. And that's the second reason why I call them ultimate field effect transistors, because they can give us the strongest ultimate field effect for best transistor characteristics. So with that, let's continue our introduction. I already started. So the scaling of single gate planar devices has been continuing for more than 5 decades. Okay. And they were actually very successfully scaled for many, many years, simple geometry scaling. However, that geometry scaling, which is the base for Moore's law, which I assume all the attendees that are listening to this talk know about, is essentially based on that scaling, right? So the transistors have to become smaller and smaller, roughly every 1.5 to 2 years, so that we can integrate more of them onto our chips, hopefully without increasing the cost too much. To improve performance and functionality, right? That's the whole idea of Moore's law. It was going very well, but starting with around, let's say, when you go below 130 to around 100 nanometer and below, it became increasingly more difficult to actually scale these devices. That's why we start to see some changes in the material. Like germanium, for example, came into the silicon to be able to enhance the mobility of carriers to give us better performance devices. This is called straight silicon technology. 2 generations later, at the 45 nanometer CMOS technology, we saw some more dramatic changes in the material, like the polysilicon, which was used in all these devices as the gate material, was replaced by metal gate, again, primarily for performance. And under the metal gate, in this MOS structure, right, we have an oxide separating the metal gate from the silicon semiconductor underneath. This all changed. It used to be silicon dioxide in these older technologies, but starting with 45 nanometer, industry switched to a better dielectric material, a better insulator with a higher dielectric constant. Okay, that's what this high K means. So these material changes allowed us to continue scaling for a few more generations, okay? But after 32 nanometer, basically, even with these material improvements, scaling of the single gate planar devices became pretty much impossible, okay? Because as you scale these devices to smaller dimensions, the short channel effects are becoming more pronounced. Drain-induced barrier lowering is increasing, subthreshold swing is increasing. These are parameters that are used to characterize transistors. In other words, these switches, these transistors are becoming more difficult to cut off when we don't need them, which means the leakage currents are increasing in each new technology generation as we scale them. So basically, beyond 30 nanometer, even with these material advancements, material engineering tricks, if you will, scaling of these single gate planar devices was not possible anymore beyond this point. That's why Intel took a brave step, bold step, you can call it, and they dramatically changed the transistor geometry from a single gate planar device to a multi-gate vertical 3D device, we call them. Okay. Here you see the cross section of a FinFET. Here the channel is a very thin silicon fin, they call it, sticking out of the silicon wafer, and it is surrounded on 3 sides by gates. Instead of having just 1 gate on top, now you got 3 gates surrounding a very thin channel area in the middle. Okay, that's why these are called tri-gate transistors, or more commonly named FinFETs, same thing. Okay, so at 22 nanometer, Intel made this transition, and then pretty much all the other major companies, Samsung, TSMC, there are only 2 left actually other than Intel now, followed, and they are all using this transistor essentially at their leading cutting edge technologies right now. Okay, and going from 22 to 14 though, only the second generation of FinFET for Intel was not easy. Okay, as you can tell from the numbers, it took them 3 years. Now, what is Moore's law? According to a paper he published in 1970s, right, this scaling should happen every 1.5 years, not even 2 actually. But as you can see, and Intel managed to scale their technology and other top companies roughly every 2 years. They did a very good job, but because of short channel effects and scaling challenges that I will talk about today, as you can see, even with the FinFET structure, going from 22 nanometer to 14 took Intel about 3 years. They had a challenge already. And then going from 14 to 10, very famous story nowadays, right? Was a disaster for companies like Intel because it took a very long time, almost 5 years. There were a lot of product delays, and Intel lost a lot of market share because of that. If you guys are following what's happening in the semiconductor industry recently, so basically going from 14 to 10, which is only the 3rd generation of their FinFET technology, was a big problem for Intel, especially. And going from 10 to 7, that's what Intel is trying right now. As you can imagine, it's going to be even bigger challenge. We don't know when they will succeed, having this technology in the market. But looking at the recent history, it may take even more than 5 years. I wouldn't be surprised. So we will see. And then TSMC and Samsung claim they are at the 7 nanometer technology generation right now. But actually, if you look at TSMC 7 nanometer FinFET technology, the drawn gate length is about 12 nanometers. So actually, there is a big gap between what these companies call their technology is and the actual minimum feature size, which traditionally for VLSI designers like us is the drawn gate length. Okay, this gap has been there actually for several years now. All right, so the reason industry is still using these numbers, which are, I'm not even sure that actually there is any horizontal dimension at this number. I don't think so. But the reason they are using these numbers to call their technologies, to name their technologies, is because they want to give the impression that the 30% scaling trend that was continued for many, many decades is still alive. Moore's law is still alive, and they're still able to scale the technology by about 30% every 2 years. But actually, that's no longer true, as you can see from the drawn gate length actual dimensions. Okay, in Intel's 10 nanometer, as far as I know, drawn gate length is 16 nanometer, way larger, way longer. And in TSMC 7 nanometer, it's about 12 nanometer. Okay, now going beyond 7 nanometer, which is what TSMC and Samsung are trying right now, Intel is even not there yet, is going to be even a bigger challenge. Okay, and because when you scale these devices from 22 to 14 to 10 to 7 and to perhaps 5, you need to keep the short channel effects under control. You have to keep the drain-induced barrier lowering low. You have to keep the subthreshold swing small enough. You have to keep the leakage current small enough to be able to do, and you have to also enhance the on current density so that you can design faster chips with these scaled transistors. So for that, what do you need to do? You have to make these FinFETs taller and skinnier. Okay, so the height divided by the width is called the aspect ratio of these devices. Okay, this height divided by the width of this device. That ratio is essentially increasing in each new technology generation, which means these devices are becoming increasingly more difficult to actually etch and fabricate in each new technology generation. That was exactly the challenge for Intel, going from 14 to 10 and going from 10 to 7. Of course, the challenge is going to be even bigger because they're going to need even taller and even skinnier fins that are going to be very difficult to fabricate. So, so what's the solution? Okay, so I strongly believe that FinFET scaling maybe is going to continue one more generation, but in the very near future, I strongly believe that it has to be replaced by a better transistor with stronger field effect. Okay, and of course, gate-all-around transistor is the first one that comes to mind, which is better than FinFET, as I will show today with numbers. However, we will in this talk go even beyond that. By 3D stacking of nanowires, you can actually have even better switches than gate-all-around transistors. Okay, so in the not so distant future, I believe that either gate-all-around transistors or 3D stack nanowire based transistors are going to replace FinFETs, and we will see these dimensions, these technologies in the future with that kind of device. So what's the problem with FinFET? Now let's see some numbers after that introduction. Here you see Intel 22, 14, and 10 nanometer technologies, drain-induced barrier lowering and subthreshold swing parameters. Now, I'm assuming everybody knows these. If you don't, ask me at the end of the talk, I will explain them, okay, if somebody doesn't know what these are, okay? But these are basically metrics that characterize switches, their quality, okay? And the smaller these numbers are, the smaller the drain-induced barrier lowering is, the smaller the subthreshold swing is, the better it is for that switch. It means that we can very effectively, very strongly cut off those transistors, those switches, in the idle mode when the transistors, the gates are not doing anything to cut off leakage. And subthreshold leakage current, of course, is a major, major problem in the electronics industry right now. So if you look at those numbers, this gray is the subthreshold swing, this light gray is the DIBL, drain-induced barrier lowering, the darker gray is the subthreshold swing. As you can see, going from 22 to 14 to 10, and then to 7, this is from TSMC, and then to 5, this is our own technology that we have developed. All of them are FinFETs, and we developed our 5 nanometer technology based on International Technology Roadmap for Semiconductors guidelines, as well as some published papers. Okay, so we developed this technology, but others are from industry. So as you can see, the drain-induced barrier lowering is increasing at an alarming rate as we scale these FinFET technologies. These are all FinFETs. Okay, and the subthreshold swing is also going up at an alarming rate. What this means is, although FinFET, here you see the cross-sectional area of a FinFET where this thin channel is surrounded by gates on all 3 sides. It's a tri-gate device. This is the cross-section. Basically, this is the channel. You're looking into the channel. This is where the electrons are flowing, okay, into this channel area, right? So this device, of course, is a better field effect transistor than the traditional single-gate planar MOSFETs. But as you can see at these dimensions, this is nanotechnology now, even FinFET is in trouble. Its characteristics are rapidly degrading as we scale it to 7 nanometer and beyond. Okay, and here you see some more details about these technologies from Intel and TSMC and our 5 nanometer technology that we have developed, all of them FinFETs again. And this is what I was talking about. If you focus here, You can see the height and the width of these fins, how they were scaled as Intel, for example, went from 22 to 14 to 10 nanometer. As you can see, the aspect ratio, which is this number divided by this, is increasing at a very high rate in each new technology generation, which means these fins are becoming skinnier, thinner, and taller. And that's why they are becoming more and more difficult to fabricate. And that's exactly why Intel had to wait 5 years to take this step, right? Once again, in Moore's law, this was supposed to happen in 1.5 years. But as you can see nowadays, it's 5 years or maybe even more. In the future, it will be the case, okay? And the same story for TSMC, very high, aspect ratio in their 7 nanometer FinFET technology, which is a major, major problem for fabrication. And so gate-all-around transistor can be viewed as an evolutionary step from the FinFET. Here you see the 3D view of FinFET, where the gate is surrounding the thin channel area on 3 sides. And here you see the gate-all-around transistor, where the gate is surrounding the channel area on all 4 sides. That's why this is called gate-all-around, okay? And these are the cross-sectional areas of the channel area. In gate-all-around transistor, you got this additional gate at the bottom, which gives you stronger field effect, which is, of course, very good for transistor characteristics. Here you see the comparison of FinFET and gate-all-around transistors for the exact same drawn gate lengths, okay? And here we are comparing DIBL, drain-induced barrier lowering, and subthreshold swing parameters. Just pick any number, for example, let's say 5 nanometer, because I'm going to focus on 5 nanometer technology today. So you just look at 5 nanometer. As you can see, the drain-induced barrier lowering and subthreshold swing of the gate-all-around transistor technology are much better than the FinFET technology. Much smaller. Smaller means, in this example, better. Okay, it means it's a much better switch. So that's one way to look at it. Another way is scalability. For example, you can just draw a horizontal line here. Okay, let's say you have a target DIBL that you're happy with. Let's say it's something like this. Okay, now as you can clearly see, let's draw a line here. You can get that DIBL with a FinFET that's 5 nanometer in drawn gate length. Alternatively, if you use a gate-all-around transistor technology where you put an additional gate at the bottom, stronger field effect, you can actually afford now to scale the drawn gate length to even 4 nanometer, and you can get some very similar, even less actually a little bit, drain-induced barrier lowering. So this switch is actually better than this, and it has got also significantly smaller drawn gate length, which means these chips are going to be much more compact as compared to a FinFET-based chip, and also providing even slightly better characteristics, as you can see. So that's another way to look at it. So if you look at data like this, you can safely say that gate-all-around transistor is a much better switch than FinFET. That's why there's a very good chance that actually it could replace FinFET, okay? But what is more interesting for today's talk is, what if we have stacked nanowire structures, okay? Because these structures could have some advantages even as compared to the gate-all-around transistor structure, okay? And that's what I'm going to be focusing on in today's talk. Few seconds of tea break. By the way, Claudio, you guys can hear me and see me very well, I'm hoping. I cannot hear and see anybody, but anyways, let's continue. All right, so now these are the 4 main primary technologies that we are going to be comparing. This is the FinFET. This is the gate-all-around device. I'm going to be looking at a stack of 2 nanowires primarily in today's talk. Now, you can do it in 2 different ways. You can separate those stack of nanowires with just an insulator in the middle without a gate in the middle. So the gate is only at the perimeter. Or you can put an additional gate in the middle as well for even stronger field effect, okay? And I'm going to call this device stack of 2 nanowires, shortly as 2N. And if I put a metal gate in the middle as well for even stronger field effect, then I'm going to call it stack of 2 nanowires with a metal gate in the middle, or shortly as 2NM. Okay, so these are the 4 different technologies that I will compare. First of all, device characteristics. I will assume they're all minimum sized, same silicon area. And I will also characterize some test circuits that are designed by these with these minimum sized devices. I will talk about some interesting characteristics of those test circuits as well. And then in the later part of my talk, I will also talk about sizing in these 3D devices, because sizing is actually not straightforward in FinFETs and gate-all-around transistors. So I will talk about sizing, how do we design these devices for higher on current, and then the stacked nanowire devices also have some advantages for sizing as compared to FinFETs and gate-all-around transistors. I will also talk about them later. Okay, so this is our presentation plan. And now let's dig deeper into this 5 nanometer stacked nanowire transistor technology. Once again, I will first start with minimum size devices and test circuits. Again, these are the 4 technologies we are comparing. Some technology details are given here, like we will constrain the height of the fin to 19 nanometer in this study. And the width of the fin is going to be 3 nanometer. And we will design the gate-all-around S2N and S2NM. These are the 3D stacked nanowire devices for the exact same height. So in other words, we will constrain the device layer thickness, okay, for a fair comparison. So for example, in S2N, stack of 2 nanowires, no metal gate in the middle, we will assume that the distance from the lower end of the lower nanowire to the top of the upper nanowire is going to be 19 nanometer, exactly same with the height of the fin in FinFET and GAA. Same constraint here for the lower end of the lower nanowire in S2NM to the upper end of the upper nanowire is again going to be exactly 19 nanometer. That's a constraint, okay, which will have some implications, as you will see when I present the data. And this is all simulation. We did not fabricate anything. I'm not a fabrication expert anyways, but I love doing technology computer-aided design. And we are using Silvaco simulators for the study. Temperature is 80 degrees centigrade, which is a typical hotspot temperature in today's multi-core processors. Remember, we are very much worried about leakage currents. That's the primary motivation for looking into these alternative technologies anyways. That's why we are going to be assuming this worst case temperature, typically the hotspot temperature. And the supply voltage we are assuming is 0.6 volts. So with that now, let's start talking about the parameters. First, DC characteristics of these technologies. So let's first look at the on current. Now, when I say on current, we turn on the device and we apply maximum VDS in NMOS, for example, to get the maximum saturation current. Okay, so that's the on current that we are talking about. So if you look at those on current values for FinFET, gate-all-around transistors, stack of 2 nanowires, and stack of 2 nanowires separated by a metal gate in the middle, these 4 different technologies, you see this picture. So as you can see, the on current of gate-all-around transistor, as expected, is actually significantly larger than the FinFET, about 7% larger. Why is it larger? Because the field effect is stronger. You got this extra gate at the bottom. I would like to again highlight one thing here. The comparison is completely fair. They all have the exact same silicon area. Not only that, even the height of the silicon layer from the bottom to the top is identical in all of these devices. In other words, we are assuming the same, again, device layer thickness. That's very important. So with that, basically, the gate-all-around transistors producing about 7% higher on current when you turn it on because of stronger field effect. Now, if you look at S2N, you will find this interesting. Is the field effect stronger in S2N compared to FinFET? Absolutely. But as you can see, the on current is reduced, about 17%. Now, some of you may be confused. How come the on current is going down if it is stronger field effect? The reason is the constraint in the height of the silicon. Now, from this edge to the top is 19 nanometer. We constrained it. Now, if you want to divide this fin into 2 nanowires and put an insulator in the middle, inevitably now the cross-sectional area of the channel is smaller, right? The cross-sectional area of the S2N channel is smaller than GA and FinFET. That's why the on current of S2N, despite the stronger field effect, is about 17% less than FinFET. So there's going to be some speed, therefore, concern, which is related to on current, as you will see. And S2NM, the degradation is even more, about 30%. Why is S2NM, which is the strongest field effect transistor, as I've been saying since the beginning of my talk, right? We put this metal gate in the middle. The field effect is even stronger than S2N, even stronger than GA, even stronger than FinFET. So how come though the current is the smallest on current? Well, because again of this height restriction. If you want to now have 2 nanowires separated by 2 layers of insulator and the layer of metal gate in the middle, now the cross-sectional area of that channel is the smallest in the set. Among these 4 devices, the cross-sectional area of the channel is smallest in S2NM, which means the channel area resistance is actually highest despite stronger field effect. And that's why the on current is significantly reduced by about 30.5% as compared to FinFET under identical silicon area considerations. Now, if you look at the off current means, of course, subthreshold leakage in this study. We are again looking at the worst case scenario with maximum drain to source voltage in NMOS, for instance. And the maximum voltage is determined by the supply voltage, which is 0.6 volts. and temperatures again 80 degrees as well. So this is like a worst case analysis for subthreshold leakage current. And you see those comparisons here, and that's where the attraction is, okay? So as you can see, going from FinFET to gate-all-around to stack of 2 nanowires to stack of 2 nanowires separated by a metal gate, the leakage current is going down significantly, okay? GAA, first of all, is quite attractive. When you turn it on, it increases the on current by about 7%. When you cut it off, it reduces the leakage current by about 57% as compared to FinFET. What else do you want in life, right? So it's a better switch. There's no question than FinFET. And if you look at S2N, the leakage is even further reduced because of, again, 2 reasons: stronger field effect and smaller cross-sectional area of the channel, which is reducing the leakage by about 69% as compared to FinFET. And S2NM, of course, is the champion for leakage: minimum cross-sectional area of the channel, maximum field effect, very strong like cut-off transistor. When you don't need it, you can just very strongly turn it off, which is going to minimize the leakage. So it's reduced by about 83% as compared to FinFET. Now, of course, on current and off current are both important, right? For chip design in digital systems nowadays, we care about both. That's why what device designers do is they look at also the ratio of I-on to I-off, which is a metric used for quality measurement. So if you look at I-on over I-off ratio of these minimum size transistors, you see that I-on over I-off ratio is much higher in these 3D stack nanowire and gate-all-around transistor technology as compared to FinFET, okay? At high temperature, of course, these values. At low temperature, the values can further increase, but at high temperature, at the worst case, again, as you can see, S2NM I-on over I-off ratio is far better than everything else, actually, okay? So that's why this is the best switch from that point of view. And of course, this ion degradation is going to be a concern for speed, but especially for low power applications like your smartphone, battery lifetime is very important. Leakage reduction is very, very important. Speed is not that aggressive, speed requirements. For that kind of applications, I think these stacked nanowire devices, especially this one, because of this very high I-on over I-off ratio, is quite attractive. And then if you want to have a very high speed chip for a server or whatever, then you may consider GAA as well, which is quite attractive, okay? Decent I-on over I-off ratio, very low I-off, high I-on compared to FinFET. And now these leakage values that I presented are, of course, also supported by the drain-induced barrier lowering and subthreshold swing values. So again, if you compare these 4 different technologies, minimum size for subthreshold swing, as you can see, as you go from FinFET to GAA to stack of 2 nanowires to stack of 2 nanowires with the metal gate, the subthreshold swing is indeed reduced significantly. So the switch is becoming better and better as you go in this direction. And similarly for drain-induced barrier lowering, there's a significant reduction in drain-induced barrier lowering as you go from FinFET to S2NM. So S2NM, drain-induced barrier lowering is about 31% less, and its subthreshold swing is about 18% less than FinFET. What this means is this is a much better transistor, much better switch that you can cut off and really, really reduce the leakage, as you saw in the previous slide. Now let's start looking at some test circuits with these devices, okay? First, I'm going to look at some minimum sized inverters with these 4 different technologies. And this is our test circuit here. We are looking at the delay as well as the input capacitance of this inverter highlighted here. So if you look at the input capacitance of this inverter with minimum size PMOS and NMOS inside, as you can see, and as kind of, again, expected, gate-all-around transistor input capacitance is higher than FinFET, okay? So why does this device, although they got the exact same silicon area, they're all minimum size, why does it have more input capacitance? Because you got an additional gate at the bottom, more coupling capacitance to the channel as well as to the source and the drain. As a result of that, you will see about 14% higher input capacitance inside with an inverter designed with GAA versus FinFET, okay? And S2N and S2NM, they both reduce the input capacitance as compared to the FinFET. One thing you can find interesting here is that S2NM input capacitance is actually higher than S2N, okay? You may ask why. As I said, a few minutes ago, because the cross-sectional area here is actually bigger than here. I mean, the silicon area here is bigger than here. You may think there will be more coupling capacitance and more input capacitance, but actually the answer is no, because there is an additional gate here in the middle, right, in S2NM, which is giving the strongest field effect, but it's also causing more input capacitance. Nevertheless, still the input capacitance is about 10% less than FinFET, as shown here. But compared to S2N, this is bigger. And now if you look at a propagation delay of that minimum size inverter, that's also interesting. GAA is the fastest in the set. So GAA inverter is about 28% faster than FinFET inverter. And the second best is S2N, which is 25% better, faster than the FinFET-based inverter. And S2NM is actually slower. So now you see the trade-off, right? S2NM was producing the lowest leakage, highest ion over IOF ratio, smallest DIBL, smallest subthreshold swing, all good. But of course, you got to lose something, right? What do you lose? It's somewhat slower than the FinFET-based inverter, about 7 or 8% slower. Why is it slower? Because on current is significantly reduced, right? Despite the fact that capacitance is less, on current is also less significantly. That's why the delay is actually increasing, okay, despite smaller capacitors. And now if you look at the voltage gains, the DC characteristics, V in, V out curve, DC characteristics, if you look at that slope, the maximum gain point, in FinFET, it's about 24.8. That's the lower end, the lowest, the worst. And the gate-all-around inverter is the highest, the best. It's about 72, 73 gain, okay? S2N and S2NM are also much better than FinFET, much higher gains. They're, though, not as good as GAA, okay? Now, this higher gain of S2N, S2NM, and GAA is actually very important because it means that the noise margins are going to be wider. So it means that the circuits that you're going to design with these three technologies are also going to be more robust, okay? They will be able to tolerate more noise as compared to FinFET-based design. And I will actually talk more about that when I talk about memory circuits. We will get there, okay? And you will see actually, indeed, these technologies have some noise immunity advantage as well. Now let's talk about energy consumption in the active mode. And the GAA-based circuit, although it was much faster than FinFET, it's also consuming more energy because of higher input capacitors primarily, about 22% higher energy in active mode as compared to the FinFET-based design. And the interesting thing here is S2N and S2NM are able to actually reduce the energy consumption in the active mode because of lower capacitance, primarily as compared to FinFET. And here, S2N is probably the most interesting one because it's both faster and also more energy efficient than FinFET in the active mode. So if you look at the minimum size inverter, actually, S2N is both faster and more energy efficient than the FinFET inverter. That's kind of interesting. Now, of course, these characteristics that I've been looking at so far, of course, give us now, if you're a circuit designer, you probably started thinking about it already, give us some opportunities for voltage scaling, right? If I have a stronger field effect device that can produce more current, that has got some speed advantages, and since energy consumption is very, very important, even in active mode for us, why don't we just now start thinking about doing some voltage scaling with these technologies that cannot be possible with the FinFET technology to be able to improve the energy efficiency, right? So, for example, the GAA, gate-all-around based inverter, when it is designed for the same supply voltage, 0.6 volt, with the FinFET, as I said, it is much faster, but it also consumes more energy in the active mode, right? But then, since energy is very important for us, why don't I scale the supply voltage to 0.5 volts, right? If you scale the supply voltage of GAA inverter, minimum size, to 0.5, and if you compare it to a FinFET inverter operating at 0.6 volts at higher supply voltage, this GAA inverter is still faster by about 13%, and now energy is also less by about 23%. So you could actually make it faster as well as more energy efficient by scaling the supply voltage. So that's the second interesting aspect of these technologies, okay? So it's not just about leakage reduction. So by voltage scaling, actually, you could also have some advantages even in the active mode for energy consumption. And similar arguments for S2N, stack of two nanowires. If you scale the supply voltage of this minimum size inverter to 0.49 volts, its propagation delay is about the same with the FinFET inverter that operates at 0.6 volt. So now these two inverters at two different technologies give you about the same speed, but now look at the energy consumption with the S2N inverter. It's almost 54% smaller than FinFET in active mode. We are not talking about leakage right now, okay? So active mode energy consumption is about 54% less thanks to voltage scaling, while providing almost the same speed, no speed degradation, dramatic reduction of energy consumption. We also designed 5-stage ring oscillators with these 4 different technologies. and we adjusted the supply voltage of these ring oscillators. All of them, again, are composed of minimum size inverters to achieve almost the same switching frequency, okay, about 97, 98 gigahertz, as you can see. What do you see? Because of voltage scaling with S2N, it's providing even slightly higher switching frequency than the FinFET ring oscillator, with about almost 28% reduction in energy consumption in the active mode. And S2NM also has got some energy advantages, GAA as well, compared to FinFET, but S2N is the champion here, most remarkable savings. And now if you look at leakage of the inverters now, before I looked at the leakage of devices, now if you look at the leakage of these minimum size inverters, so if they're idle, you can get the input either low or high. We looked at both of them. And if you look at the average leakage, FinFET, as expected, is the highest, about 9 picowatts. And S2NM, again, as expected now, hopefully, after all this discussion, is the lowest, 2 picowatts, much, much smaller, about 78% smaller than the FinFET leakage in idle mode, which is going to give you, again, a lot of savings and better lifetime in these kind of smartphone-like applications. And GAA, gate-all-around, and S2N devices are somewhere in the middle. Again, of course, much, much smaller than FinFET, but S2NM, the ultimate field effect transistor in the set, is the champion for leakage. Now, we also designed minimum size memory cells, static random access memory cells. These are 6 transistors standard. Minimum size means what? All the cross-coupled inverter transistors and the bit line access transistors are all minimum size, okay? And we designed 4 kilo binary bits, 64 row, 64 column memory arrays with these cells. And we looked at some interesting characteristics like static noise margin, read and write delays, and leakage power in idle mode. As you can see, GAA is the champion in pretty much everything except leakage, okay? It provides the strongest data stability. Now, this should not surprise you if you're listening carefully, because remember, I talked about voltage gain, right? I talked about noise immunity advantages of these technologies. There you go now. If you design memory circuits with these, since gate-all-around technology provides the highest voltage gain, the static noise margin, as expected, both in hold mode and read mode, is the best, actually, okay, among the set. And FinFET is the worst. That's also kind of expected. S2 and S2NM are, of course, better than FinFET for data stability, but GAA, gate-all-around, is the champion. And GAA is also champion for speed. Both the read and write speed are the best, the fastest. And FinFET is also the worst for leakage, as expected, highest. Now, S2NM is the champion for leakage, okay? For leakage power consumption, it's the smallest. If you really care about leakage, you want to minimize the power consumption in idle mode, in your cache, in your processor, for example. S2NM is, again, quite attractive, but it comes with some speed penalty. As you can see, it's also the slowest for read and write operations, okay? If you don't mind, if this kind of speed degradation is okay, if you want to save a lot of leakage power, if you want to extend the lifetime of your smartphone, this is the technology to go. If you want the strongest data stability, most stable cache, fastest cache, you better go with GAA. Is FinFET good for anything? Not at all, okay? So hopefully that point is now becoming clear. Now, Claudio, how much time do we have? Can you please write and chat maybe, or say it? Oh, I see here live 41 minutes, but is it just my time or includes your time? I'm not sure. But anyways, I'm going to continue as long as you let me continue, okay? Hopefully you guys are there.
Yes, you have around 15 minutes, so don't care about that.
Oh, okay. So time is okay, right? All right, then. Let's continue. I'll try to finish the presentation. Okay, good. Thanks. So next, let's talk about transistor sizing, which is also very interesting, actually, in these 3D devices. It's not straightforward. So far, we are looking at single FinFET and single fin gate-all-around transistor, right? So these issues exist in FinFET as well as gate-all-around transistors, okay? Sizing is not straightforward. So we are looking at this device essentially, 19 nanometer fin height, 3 nanometer fin width, okay? And these are the minimum size devices that we were looking. But minimum size device, of course, is not going to provide enough current everywhere on your chip, right? Sometimes you will have areas on your chip, gates, circuits, where you will need more on current, which means you will start thinking about now sizing your transistor to increase the on current. Now, how can I increase the on current of a transistor that looks like this, a 3D, fin sticking out of the wafer? And so what you can do is, first thing that can come to your mind is, okay, what if I increase the height of the fin on the chip wherever I need more current? That's really not a feasible idea because of two reasons. First of all, you cannot just arbitrarily increase the height of your fins across your chip, because the device layer, which is a single layer, I'm not assuming 3D integration here, by the way. I'm assuming like a conventional chip integration where there's only one device layer, okay? And that device layer is going to have a certain thickness, height. So you cannot obviously arbitrarily increase the height of your fins across your chip wherever you need more current. That's not feasible. Another reason why this is not feasible to increase the height is because as you make these fins taller and taller, even if you don't care about, let's say, the thickness of that layer, the aspect ratio is increasing, which means they are becoming more and more difficult to fabricate. The etching is becoming an issue, as I mentioned at the beginning of my talk. That's the second reason why actually you cannot increase the height of your fins, okay? So this is not an option, although it's an idea. It's not feasible. The second idea you can explore, okay, let me keep the height same, but let me adjust the width, right? Instead of having a very thin fin, 3 nanometers, I can make it bigger, wider. This is not a good idea too. There's a reason why this fin is only 3 nanometers in our technology, because we want to control the short channel effects. We want to control DIBL and subthreshold swing. We want to control leakage currents. If you move these side gates in this tri-gate structure further away from each other, you're essentially losing control, electrostatic control, charge control in the mid segment of this channel is degraded as you move the side gates further away from each other. Okay, so that's why making the fins wider is definitely not an option either. Then what do I do to increase the on current? The answer is you got to add more fins. Keep the fin geometry constant across your chip, but wherever you need more on current, add more fins into your transistor, make it a multi-fin device. The same argument for gate-all-around transistor, exact same issue. Okay, so if one fin is not providing enough, next step is 2 fins. If that's still not enough, next step is 3 fins. So basically now sizing and the current are quantized with the number of fins. Okay, this is called quantized sizing requirement in FinFET, which is a major disadvantage because, as you can imagine, if you want to fine-tune your own current, it's not possible in this technology, which is a concern for integration density, chip size, and cost. Okay, and that's why FinFETs have this problem, and as long as we use them, we will have to live with this problem, this quantized sizing issue. Another advantage of these 3D stack nanowire structures is sizing compared to FinFETs. Basically, if a minimum size stack of 2 nanowire S2M, for example, is not providing enough on current, you can make those nanowires wider. Now, this is not the same thing as making these fins taller. Okay, what we are talking about right now is a horizontal increase in the width. And in the horizontal dimension, we can etch whatever we want, okay? The only limit is the manufacturing grid of the technology. So we can essentially adjust now the widths of these nanowires with very, very small steps, which is not possible with FinFET or gate-all-around transistor technologies, okay? With the 3D stack nanowire technology, we have this flexibility. We can fine-tune the widths of our nanowires to adjust our own current. However, there's a catch here. So before the catch though, so this flexibility is very good for silicon area efficiency. That's an absolute advantage compared to FinFET and GAA. However, there are limits here, as you will see with the numbers soon, because again, there are like 4 gates, right, surrounding these 2 nanowires in S2N structure, and the 2 side gates are moving further and further away from each other as you make these nanowires wider, which means the field effect is actually becoming weaker as you make these transistors wider to produce more on current, which means when you cut it off, it's going to actually produce significantly higher off current, okay? So the leakage advantages of this device architecture are kind of degraded, and it may even vanish, and as you will see with numbers soon, they may actually even produce more leakage than even FinFETs, okay, if you're not careful about the sizing. So that's an issue as well with these 3D stack nanowire technologies that we will talk about. So here now, next, I'm going to look at FinFET with 2 fins as my benchmark circuit. So far, I was looking at single fin FinFET, minimum size. Now I'm going to look at a 2 fin FinFET that can produce almost double the on current. And I'm going to now design the gate-all-around transistor with the exact same geometry, exact same area, and with 2 fins. And I will design S2N and S2NM with two different constraints. In the first design, I'm going to design them for, again, identical silicon area with this 2-fin FinFET, okay? And if you want to equalize the area of S2N and S2NM to this 2-fin FinFET, you got to make these nanowires 14 nanometer wide. Now, in the minimum size device, remember, this was only 3 nanometer. Now I am almost 5 times increasing that width, which is going to have some implications for leakage current, as you will see. And in the second constraint, second design, I will design inverters with S2N and S2NM for same average propagation delay as the inverter designed with 2-fin FinFETs. So far, I was looking at minimum size inverters. Now I'm going to change to somewhat bigger inverters that can produce more current with 2-fin FinFETs. And S2N and S2NM are going to be designed for similar average propagation delay. Now, if you design S2N transistors to match the speed of a 2-fin FinFET based inverter, you need to make the width of the nanowires about 4.6 nanometer. Okay, and alternatively, if you want to make S2NM based inverter similar speed with the FinFET, 2-fin FinFET based inverter, you got to make the nanowires 5 nanometer wide. Now, again, this may confuse some of you. This is a stronger field effect device. How come it's bigger than S2N? The nanowires are wider. Again, the answer is in the cross-sectional area. Remember, the distance from the top of the upper nanowire to the bottom of the lower nanowires restricted still to 19 nanometer in all these designs. I'm not forgetting that restriction, okay? The thickness of the layer is fixed. As a result of that, if you want to put 2 layers of, insulator, additional layer of metal gate in the middle, inevitably the cross-sectional area of these nanowires is reduced compared to S2N. That's why to compensate and to provide similar speed, you have to now make those nanowires wider. You got to now go in the other direction, horizontal direction, make them wider. Instead of 4.6, you got to make them 5 to match the speed. Okay, that's the reason. And okay, now with that, now let's take a look at the device characteristics first. Start with the good news. Gate-all-around transistor with 2 fins, identical area with the FinFET, exact same silicon area, is when you turn it off, it's reducing the leakage by about 63% compared to FinFET. Alternatively, when you turn it on, its active current is about 9% higher. So on current and off current are both significantly better than a 2-fin FinFET. Now look at S2N and S2NM. They are both producing much higher on current when you turn them on. Interesting. Okay. Why is it the case? Because they are both now very wide nanowires, 14 nanometer, exact same silicon area with this 2-fin FinFET. So these are now very wide structures. Therefore, they are producing a lot of current when you turn them on, even more than FinFET. That's good. But when you cut them off, look at the y-axis, their leakage is much, much worse than FinFET now. Okay. This is something that nobody has been talking about so far. Everybody's talking about the sizing advantages of these stacked nanowire devices. But as you can see, you got to be very careful with that because field effect is becoming weaker. Leakage current is increasing if you make them too wide. Okay. As you can see, leakage can be 4 to 16 times larger than FinFET. These are per device values, of course. And now if you look at the inverters and compare them, inverters that are designed for identical area with the 2-fin FinFET based inverter, this is what you see. S2N and S2NM, because the on current is much better, they are providing much smaller propagation delay, much faster switching speed. S2N is the champion. It's about 35% faster than FinFET with 2 fins, identical silicon area. Very interesting. And its energy consumption is also less because of smaller capacitance compared to the FinFET-based design. Its energy consumption is about 22% less in active mode energy I'm talking about here as compared to FinFET, which is faster and also more energy efficient. S2NM is also faster, although not as impressive as S2N, but its energy consumption active mode is slightly higher than FinFET. Okay, and if you look at the gate-all-around based inverters, again identical area with the FinFETs, 2-fin each of them, the speed is about 9% better than FinFET, but the energy active mode is also about 10.5% higher because of larger capacitance. Okay? And finally, if you look at the leakage power consumption of these inverters that are designed for identical area with the 2-fin FinFET-based inverter, this is what you see, the disaster right here. So everything was looking good in the active mode now, but in the idle mode, as you can see, since the nanowires became very wide, since the field effect became very weak now compared to a minimum size device, the leakage current now is actually 18 times not percent, 18 times higher in S2N as compared to the FinFET-based inverter. Okay, so all those leakage advantages are gone, as you can see. Even with S2NM, leakage is much higher than FinFET. And GA is still attractive here as well. It reduces the leakage power by about 57% as compared to the FinFET-based design in the idle mode. And next, we also designed these inverters for similar speed. Let me just briefly talk about that too. So when you design them for, again, similar speed with the FinFET-based inverter, now the nanowires don't have to be very wide. In case of S2N, it can be only 4.6 nanometer wide. In case of S2NM, only 5 nanometer wide. As you can see, the propagation delay is almost same with the FinFET inverter, but the energy consumption in the active mode is much less. Okay, and S2N is again the best, 46% less than FinFET, and S2N is also pretty good, about 40% less energy consumption in the active mode with almost the same speed. And furthermore, since now these devices are narrow, much narrower, they also give you a lot of area savings as compared to the FinFET and GAA-based designs. Okay, so they are faster. They consume, they're not faster, I'm sorry. They have the same speed. They consume less energy in the active mode. Furthermore, they're also much more compact. They give about 22 to 23% savings in area, which is very, very important for chip area and cost. And if you look at leakage power in idle mode for these inverters that are designed for, again, identical speed with the FinFET with 2 fins, the leakage of S2NM now is also better. It's about 64% approximately less than the FinFET-based inverter. S2N, though, is, despite the fact that it's much smaller now, right? What is the width in S2N? 4.6 nanometer. Still, since the field effect is now still worse than a minimum size device, the leakage is actually somewhat higher, about 14% higher than the FinFET-based design. Okay, so the leakage is still an issue, even when you design these for similar speed, at least for S2N. But for S2NM, thanks to the strongest field effect, leakage advantages are also back if you're careful with sizing. All right, with that now, I'm going to conclude my talk. It's been 55 minutes, so let's try to finish. At the beginning of my talk, I mentioned the technology scaling challenges with the current most advanced device technology commercially available, that's FinFET. I mentioned that the FinFET characteristics are rapidly degrading with technology scaling. The short channel effects are becoming worse. DIBL is increasing, drain-induced barrier lowering, subthreshold swing is increasing, leakage currents are going up. To be able to control these, the device aspect ratio has to continue to increase in each new technology generation, which means FinFETs are going to become increasingly more difficult to fabricate. That's why they are very likely to be replaced with a better, stronger field effect device. Gate-all-around transistor, of course, is one candidate, but what is even more interesting for us in this talk is stack of nanowires. So if you compare FinFET and stack nanowire circuits that are designed for identical silicon area, stack of 2 nanowires without a metal gate in the middle was looking the best, and it was enhancing the output speed by about 35% while lowering the energy consumption by about 22% as compared to a FinFET-based inverter under identical silicon area constraints. And alternatively, if you design FinFET and alternative technology circuits for identical speed, S2NM inverter was looking pretty good. It was lowering the active mode energy, silicon area, and the idle mode leakage power all very significantly as compared to FinFET-based inverter while maintaining speed. And in addition to these scaling challenges, quantized sizing requirement in FinFETs and gate-all-around transistors is also an issue for integration density, chip area, and cost, and they will continue to be important concerns, of course. Another important advantage of these 3D stack nanowire devices is that you can actually fine-tune the strength of the devices by fine-tuning the width of the devices in the horizontal direction, which is very good for integration density, area, and cost. But as you make the nanowires wider, field effect is becoming weaker, and the leakage can be an issue. And so this is a continuing study. We are now looking at adding more layers of nanowires and thinner nanowires to improve characteristics. So far in this work, I looked at layer stacks of 2, but you can make stacks of 3, stacks of 4. You know, Intel is talking about stacks of 4, for example, nowadays. So if you look at stack of 3, you can look at S3N. Let's call this an S3NM with metal gate in the middle. If you look at the data of S3NM, for example, that's kind of interesting. Compared to a FinFET, again, with 2 fins, when you turn it on, it produces much higher on current, and when you cut it off, it produces much smaller off current. So both the on current and the off current can be significantly better than FinFET if you add more layers to the stack. Now, what's happening if I add more layers to the stack? The nanowires are becoming thinner. That's why even if you make them wide, as you can see, you can still control short channel effects and leakage. That's the idea, okay? But of course, when you add more layers, right, to the nanowire stack, fabrication is also, of course, going to become more challenging and cost can go up. That's other side of the story. And so we are now exploring these thinner and wider nanowires with increased number of layers in the stack for higher performance with less leakage. We will also compare to even larger FinFETs. So far, I talked about minimum size and FinFETs with only 2 fins, right? But what if FinFETs with 3 fins, FinFETs with 5 fins, 10 fins, very wide transistors that can produce a lot of on current? If now we design these 3D stack nanowire devices to match that kind of very wide FinFET currents, how are the other characteristics going to look? As you can imagine already, having that wide, nanowires in a 3D stack is going to look very bad for leakage. And that's why we are thinking about looking at arrays of 3D stacks of nanowires instead of having just one stack with very wide nanowires. This can give us better leakage current characteristics. We are going to look at that. That's the future work. And we are also looking at increasing total height of the silicon layer, right? So far, I constrained everything to 19 nanometer, but if we can actually relax the silicon height, at least in the 3D stack nanowire structures, we can actually match the FinFET current and speed with even smaller stack of nanowires that can give us further area compaction. Okay, so that's another interesting aspect that we are looking at. We will, of course, look at effect of process variations. Lineage roughness, random doping fluctuations are concerns in nanotechnology. And so they will, of course, be big concerns in nanowire devices as well. And we are going to explore those in the future. So I will finish here by thanking my former PhD student. He graduated. He is now a research fellow at National University of Singapore, Dr. Gundu. I would like to thank him for his contributions to this work. And hopefully I managed to stoke some curiosity here. If I could create some curiosity, I would like to also recommend these 2 recent papers from us that were published recently this year. If you would like to learn more about these trade-offs and these technologies, strongly recommended reading. One was published at IEEE Transactions on Electron Devices in March, and the other one was published at CASS in May earlier this year. With that, I will finish. Thank you very much.
Okay, exactly. Thank you.
Thanks, Claudio. I really appreciate it. Thanks for your patience. It was a little bit long, but
thank you very much, Professor Kursun. It was a very nice talk. We have already one question here from Enrique Kessler. I'm going to show in the slide. So, is it possible to fold the wires in 4 instead of increasing the width of 2N or 2NM devices? The way you could still benefit from the strong field effect.
Absolutely. Actually, I said it even while I was passing, but maybe I was talking a little bit too fast because there are a lot of slides. But actually, Intel is right now, as far as I know, they're actually more interested in stacks of 4 nanowires, not even 3. And that's a trade-off, definitely. You can add more layers, and the advantages, then those layers can become thinner and thinner. Actually, in a stack of 2, if you look at our design, and that's why the leakage was looking very bad when we make them wider, are kind of thick, like 8 nanometer or even more, actually, in S2, 8.75 or something like that. So if you add more layers, you can actually make those nanowires even thinner. This way, even if you make the device wider, you may be able to still have some decent leakage characteristics. But the catch is, of course, the fabrication is also becoming more and more challenging as you add more layers. That's the other side of the story. Yeah, that's my answer.
Hey, Professor Reis, there's some questions there. Professor Reis is in Rio with the CASS Rio chapter. Is there some question there?
I cannot see it. Yeah.
So we have a question here from the audience in Rio.
Professor Reis, there's some questions there. Yeah. And Professor Reis is in Rio with the CASS Rio chapter.
Yes. So Professor José Gabriel Professor José Gabriel from Federal University. So I give the floor to him. So, Professor José Gabriel from... Pode falar aí,
okay. Hi, Professor Kursun, can you hear me well?
Yes, I can hear you. Yes. Hi.
I don't know if you hear me. Thank you for the very interesting talk.
You're welcome.
Mas eu acho que tem delay.
Pode ter delay, mas vai ficar.
Yeah.
Pode perguntar.
I don't know if can we hear him as well?
Yeah.
I can hear you. I don't know whether you can hear me,
very interesting subject. You mentioned many things at the device level. I was wondering if you have some examples using a few or many devices in a chip, some kind of application.
Actually, I present some test circuits, like some inverter chains, ring oscillators, some SRAM cells. Of course, these are not some even SRAM array we designed 64 row, 64 column. So these are, of course, not very big test circuits, but for this kind of device research, they are good enough actually for benchmarking. And I don't know whether you were there during that part of the talk, but actually I presented some test circuits. We have designed some, but they were very simple, like ring oscillators, SRAM cells, etc. kind of. Yeah.
Okay, thank you. I may have missed that. I'll try to see it later on the.
Yeah, definitely. I talked about them, and if you watch the video, you will see them actually. I presented a lot of benchmark, for circuits as well.
Thank you.
You're welcome.
Okay,
Ricardo, I cannot hear you, Ricardo.
Okay.
Oh, there you go.
I have also another short question. Do you have any comparison also with FD-SOI?
No, we didn't look at SOI, but of course, I mean, fully depleted SOI is better than single gate MOSFET, right? But the thing is, as far as I know, FinFET is better anyways than fully depleted SOI. As far as I know, if I'm wrong, correct me. But that's why industry is all using FinFET now, right? So that's why we didn't look at it. I mean, fully depleted SOI would be interesting if you want to make a comparison to the old planar devices, but we are not looking there anywhere anyways, so we are just taking it from FinFET and to the future. So as far as I know, FinFET is better technology than
for some applications, industry in Europe are using FD-SOI for low power.
Yeah, definitely. I mean, there are companies that are using SOI, right? I'm not saying it's not being used, but if you look at the cutting edge technology used for computers primarily, like TSMC, Samsung, and Intel's best technology, it's all based on FinFET now. That's the current most advanced technology. And after FinFET, it's not going to be fully depleted SOI. I can just tell you, we're not going to go back. But after FinFET, where are we going is the question here. So after FinFET, gate-all-around transistor technology may come. As you saw, there are some very important advantages. But if they can be fabricated, if the yield can be kept high, I think 3D stack nanowire technology, especially for applications like these where energy efficiency is very, very important, leakage is very important, I think has a very bright future. That's why I call them the ultimate transistors. These are the devices that are going to take us to the end of the roadmap. I'm quite optimistic that we're going to see them one day. And actually, if you look at especially the patent activity recently, from Intel, Samsung, and TSMC, there's already a big competition right now between those three major companies for filing patents about this technology, which means it's coming. Okay, it means they are really convinced or they are very excited about this technology, and therefore I'm quite optimistic that it may be coming in the near future.
Okay, we have still some questions in the chat. So
I don't see them here for your information.
yeah, I can put here in the screen. So is a question from Mohammad Kaleki. Is it possible to integrate with ferroelectric materials to obtain no volatility?
Mohammed is actually a new PhD student I'm trying to take right now. And Mohammed, that's a good question. That's exactly in my mind, actually. I'm thinking about expanding this research in that direction as well. and you hopefully will be one of the PhD students working on that topic. Absolutely. So we will also try to integrate ferroelectric materials into these structures to design some non-volatile circuit elements for edge computing. That's in my mind, Mohammed. Good question. And you will do it, actually. It's coming soon.
There's another question by Almaz Shati. What is the added manufacturing cost of our round wrapping?
Almaz, I cannot give you a number about the cost, of course, but it will be a more costly technology for sure. And but to be able to continue technology scaling, and if you consider the demand for high performance computing, which is not going to become less, it will just continue to increase over the years. I mean, the whole world depends on this technology. There's a lot of money. Okay, we are talking about more than $500 billion US every year in revenues right now. It's increasing. So in an industry like this, which is ever growing, okay, towards $1 trillion US mark now, where there's a lot of money, there will be solutions. And yes, these are more costly technologies, but for high performance computing in the future, I think we will have to see these kind of more expensive technologies at some point. Remember, because FinFET is also more expensive, much more expensive than the planar devices. But 10 years ago, that transition had to happen so that we could get where we are now. And now what I'm talking about is how are we going to go 10 years, 15 years down the road to the future, right? To continue to make our computers better, we will have to make additional investment to these kind of more expensive but also better technologies. I'm confident because money is, in USA, basically, it was just a few days ago, it was approved, right? This CHIPS Act, they call it. The government is now going to provide a very significant amount of money to the semiconductor industry. Primarily Intel is going to benefit from this, of course. So, they may, with all this additional money coming in, especially from even the government now, US government, I'm optimistic that they may be able to do this, in the not so distant future.
Okay. João Antônio Martino is congratulating you.
Thank you very much, Professor Martino. Thank you very much. I appreciate it. Thank you for attending. Thank you.
And he also making some question. What do you think about fork device? He also complements fork sheet device.
Yeah. Fork devices are like are essentially based on the same technology. They are, I think, for increasing the integration density of NMOS and PMOS, like making them as close as possible on the chip, as far as I know. So it's essentially a variation of this. Hopefully they will succeed. That's all I can say. I've seen some publications recently about that technology. But actually, the underlying technology is exactly what we're talking about here. Okay, but in case of fork, basically, they're just trying to increase integration density by making PMOS and NMOS devices, as far as I know, as close as possible on the chip. And if they succeed, of course, it will be successful as well in the future for implementation, in real commercial products.
Okay. I have also one curiosity about you mentioned about the tools that you use to simulate the device, since there are many students here attending. Can you comment about these and what is the challenge of fabricating the device in the future?
Now, we are using Silvaco tools here. Silvaco has 3D simulators for process, for device, as well as for mixed mode simulations. If you want to also characterize some circuits like we did, you have to do also mixed mode simulations with tools like Silvaco's tools. So we are using the best available, commercially available. These are commercial tools that are used by industry as well. We pay a lot of money every year. We just buy the licenses and use them for our research. And of course, designing things on the computer screen is never the same with fabricating, in a fabrication facility. I'm not a fabrication expert. I admit that. So as I mentioned in my talk, my research is more on the technology computer-aided design side of it. But there were a lot of fabricated devices as well as some simple circuits in recent years, because this is a very promising technology, as I said, from industry. You can see some publications recently from Intel, Samsung, IBM on this topic, on this technology. They have fabricated some structures. Not 5 nanometer, of course. I haven't seen 5 yet. I mentioned actually, even in the FinFETs, right, in their commercial technology right now, when they say 7 nanometer, actually they're talking about gate lengths like 12 nanometer or even more. So, but we were here talking about very aggressive actually scaling. Here in this technology, when we say 5 nanometer, we mean it. I mean, the drawn gate length in all these devices, including FinFET, was exactly 5 nanometer. These are, of course, very difficult to fabricate. I mean, there's no question. It will be a costly technology. But like I said, money is also there. I mean, it's ever-growing revenue. So hopefully we will see it one day on real chips.
Okay. Okay, thank you very much.
By the way,
So,
I recommend Silvaco. Just continue your question. I've been
Yeah.
using it for many years with many students in my research group. We are very happy. It's a very nice tool. Provides very accurate simulation of process as well as device and circuit characteristics. That's a Silvaco advertisement. I'm not working for Silvaco, but since you asked, I mean, that's what we use. That's what we have been using for many years, and we are very happy.
Okay,
Silvaco.
nice. Okay. Any other question there, Ricardo? In real? No?
There is another question here.
Sure.
Yes.
Okay.
Professor Fernanda.
Hi, nice to meet you. Thank you for the talk.
Thank you very much.
Recently, I saw a presentation about variation process with the FinFETs and how there's still a lot of variation. This can be a problem. How do you see that? Can you comment a little bit on that?
Yes, actually, as I mentioned towards the end of my talk, actually, process variations, line edge roughness, random doping fluctuations are concerned in nanotechnology. That's a fact. And we have some preliminary results, okay, that I can tell you because we are already looking at it, okay. So when we combine line edge roughness and random doping fluctuations, when we look at the combined effect, I can just tell you that in these 3D stack nanowire devices and GAA, gate-all-around, things are not going to be worse than FinFET, okay? What that means is, yes, it's going to continue to be a concern, of course, especially as we go to even smaller and smaller dimensions. But what I can see right now from the preliminary results that we are still looking at right now is that it's not worse than FinFET, at least. I can tell you that, okay? But it's going to be a concern, of course, because FinFET is not, I mean, especially in these dimensions like 5 nanometer, variations are going to be a big concern for FinFET, as I mentioned, right, at the beginning of my talk, which means it's going to be a concern for these technologies as well, right?
Thank you. Thank you very much.
You're welcome. You're welcome.
Okay.
So thank you.